Thank you very much for very interesting talks. I was wondering, from like a public perspective as well, often with new technologies, something people worry a lot about is safety. I know there have been some stories of lithium-ion battery fires and so on. I wondered what kind of technological developments are happening in that kind of space, and if we're doing any work on that.
Who wants to take that one? Maybe that's one.
Shall I start on that one? So lithium-ion batteries, if you abuse them, if you take them well beyond the way in which they're supposed to be operated, can catch fire, and they can do so with quite a lot of energy. So the products that you see on the road today, the cars that you see on the road today, have been very carefully designed to make sure that those batteries are kept well within their safe operating conditions, and that they're protected in the vehicle in very much the same way that you would protect an occupant in the vehicle. So only the most extreme of events would lead you to that kind of situation. Now, the challenge that we've got is obviously to do that introduces a cost overhead and a weight overhead to the vehicle. So if we're able to develop batteries which don't have some of those failure mechanisms, we can take advantage of that by making the vehicles lighter and cheaper and have more flexibility over the design of the package. So there are technologies, so Serena mentioned earlier things like solid-state technologies, which take the volatile organic compounds, the liquids that can burn, out of the battery and replace them with things like ceramic layers or polymer layers. So there are some things that we can move forward on that, but I would encourage you to think, safety is not something that we optimize. Safety is a threshold that we have to achieve. What we optimize is how much energy or how much cost or how much performance we can get within an acceptable level of safety.
Does anyone else want to come in on that? We'll go to another question if not.
Really quickly, just on, you do see these pictures spreading really quickly on social media, right? Like of a battery on fire. Very many more cars go on fire because of petrol. So I think we should state that. But yeah, there are developments, and Faraday Institution is leading on projects to look at ceramic materials that can withstand very high temperatures and still allow for lithium to be going across your battery very safely.
And just quickly on that, on a cell level, high quality raw materials, better processing methods, improving the battery cell level drastically. But interestingly, on a pack level, you're starting to see introductions of like flame retardant materials within the pack to stop the propagation. If a cell fails, it catches on fire. You can shut that off through the management system, but actually this flame retardant material within the pack can kind of stop that propagation. But that's a real big area of R&D and interest.
Okay, yes, take a question here.
A question for Judith. If you had to pick a year, what year do you think we'll see a solid-state battery Jaguar car on the road?
Oh, that's a really interesting question. Well, there's two parts to that question. One is, when will solid-state batteries be commercially available? And maybe I've deferred to some of my colleagues, but I think that's certainly not before 2025, 2026 at the earliest. And the second is then, how quickly do we then get that into a vehicle, recognising the question before in terms of the amount of validation testing that's necessary. So one is having the cell available as a mass production cell, and the second is then making sure it's gone through all of the validation testing necessary to integrate that into a car such that it is then safe to release on sale. So there are two, so that again would take a further couple of years. So I think probably you're looking at 28, 30 as probably a ballpark. But who knows, because these things are moving so quickly that there could be a breakthrough next week and all of those are pulled forward. I don't know if you've got some...
There's still challenges to be opportunities for us to do more science to try and get all solid-state batteries to the point where they're manufactured widespread. I mean, when you look at lithium-ion batteries right now with liquid electrolytes are great because they wet everything so well, so that the interactions you have with your electrolyte and your electrodes, they allow those lithium ions to shuttle back and forth quite easily, like I showed in the video. With solid electrolytes, you're taking two solid materials and you're trying to get them to marry each other. And they may not always like each other, on an atomic level. You're going to try and get them to allow those channels so that lithium ions can move quite freely. But there's lots of ongoing work at the moment to try to develop new classes of materials that facilitate that lithium diffusion across those barriers.
Thank you. Are there any disruptive technologies on the horizon? And B, could you spend a little more time on the end of life?
Disruptive technologies. I don't know who wants to tackle that. Serena, is that one for you?
That is a really challenging question, because I think depending on who you speak to, every individual will tell you that their particular chemistry is the next disruptive technology. I think one of the things that could have the potential to be very disruptive could be additives that we put into electrolytes that help heal or protect electrodes, and they prolong the battery life so that you don't see, in your last slide, Judith, you had this, the decrease in capacity over time. And if we can come up with suitable additives that protect the battery against those sorts of degradation mechanisms that cause that decrease in capacity over time, I think that has the potential to be very disruptive.
And on that, lithium-ion batteries are getting better. So they're pushing these technologies further down the timeline, as Judith was saying. So new chemistries, new formulations of NCM is pushing even the solid state further down. And it's very important not to read the headlines that are coming from the universities, with all respect, because that's where the R&D, that's where the stuff is happening on the R&D basis. But it takes a long time to commercialize that and get it into the supply chain, and that's a really important point.
Yeah, I would say so. The word disruptive is a really salient one to use, actually. If you look at the next generations of battery chemistry that are coming down the pike at the moment, and the timeline that Judith outlined is exactly the right one. You know, nobody knows how long a battery takes to come out of academia, because it might never come out. But once it's popped out of there, there's a reasonably predictable timeline for how it gets to market, and it's the timelines that Judith described. The question of whether it's disruptive to me is, could I accommodate it within my supply chain? So in other words, if I've built a gigafactory and all I need to do is change one grey goo for a different grey goo and everything still works, and okay, the supply chain bit needs to sit in, to me that's not very disruptive. It's certainly evolutionary. It certainly improves significantly the performance of the battery, but actually the next generations of chemistries that we're working in the labs mostly fit that mold. So things like sodium-ion chemistry that could potentially reduce the cost significantly, even some of the solid states technologies could actually fit the majority of that manufacturing process and wouldn't be too disruptive. Where we start to step off that curve into something which is radically different in its design is where we start to get into things like the lithium-air batteries, which actually function in a very different way. They breathe a bit like an engine or a fuel cell. And then really you would worry that you'd made a huge investment in a massive gigafactory and suddenly it's no longer fit for purpose.
Okay, we have a question here. Can we have a microphone over here, please?
What's the strongest kind of battery you know?
The strongest kind of battery you know. Who wants to take that one?
So we work with things for motorsport applications. So the cars that Judith showed are fast, but the kind of things that we're talking about are the kind, things that run around Formula One tracks or run around Formula E tracks. And there we're actually developing the battery in a very different way, because it's not about how far the car can go, it's about how fast it can go. So we're tuning those batteries for power instead of for energy. And interestingly, the whole way that you design for the chemistry and everything else changes in order to do that. But they're still lithium-ion batteries at heart. They're just moved around a bit in the way that we designed them.
What's your name?
Max.
Max? That's a really good question, because it stumped us all, actually, because on the for a vehicle, for a car, lithium-ion batteries right now are the best that there is, and they're getting better on a cell level and on a car level, on a pack level. But things like energy storage, where you can plug your house into a battery, there are quite a few different technologies and types, flavors of batteries, including different flow batteries, even saltwater batteries have been mentioned. So that arena for powering your house is a completely open arena for batteries. Good question.
Great question, thank you. Yes, take one here.
You always see these headlines on Daily Mail and stuff saying Elon Musk is killing the world because he's mining for the materials for these batteries, but how environmentally damaging are they?
Simon, do you want to tackle that?
Cheers. Good question. I mean, from a supply chain perspective, let's look at lithium, for example. A third of lithium is coming from brine resources. Actually quite low impact, but quite intensive on water, using water from the local area. Then you look at graphite mining, it's traditional mining, it's quite dusty. But My point is, all these raw materials are coming from the same place the raw materials that make all the car components are coming from. In fact, there's a lot less components that go in an electric vehicle than there are in a gasoline vehicle, an ICE vehicle, far less. So it's another argument about the energy you put into the battery to fuel it. That's probably something for someone else. But from a battery supply chain perspective, because there's far less components and lithium coming from brine resources is quite a big component of that, I would argue a lot less environmental impact from the mining perspective. But everything's got to come from the ground, whether it's an electric vehicle or an ICE vehicle. And that's something to consider, which is why recycling is such a big part of the whole supply chain. I don't know.
Yeah, perhaps I'll just add to that. I think the key point at the end of life is that the batteries don't just end up in landfill. They have a value. And the key is, at the moment, the population of batteries that we have available for recycling or for is very difficult to make a business case on that. But it will happen over time as the amount of EVs that are in the world increases. So too will the recycling facilities to be able to, and the business case that supports the recycling will mean that we then in ideal world, we'll get to a closed loop system whereby the cobalt will be taken out of the batteries, it will then be fed back into the original part of the system, and you're in a virtual circle. And that's where we want to get to, but it will take time and it will take the volume to get there. But ultimately, there is no reason why it can't be done, because effectively you've already got your materials, you've processed it once, you don't need to spend the money to reprocess it. It's a recycling step only.
We have a question right up there, and I'm going to come back to you, sir, because I know you were waiting. Take a question up the top. I can't see you, I'm afraid. But...
Hi, I'm James Hayter. Judith, another one for you. You just touched on it. With regards to mass recycling of lithium-ion batteries, I presume at the moment there is no commercial scale recycling of the cathode materials. And to get to that stage, is it just a matter of scale, or are there some technological improvements that need to happen, or is it a case of these battery metal prices have to go higher in order to incentivize that recycling as well?
There are companies who are recycling batteries today, so it is happening already. I think it's a question of how much it becomes mainstream, and it will happen. It has to, because the amount of value that's tied up within the battery pack means that it will happen. So it is something that is happening today. It's not something of the future. It is real, and it's now.
And so the technologies that are used today, typically it's companies like Umicore that are doing this. And what they're doing is they're recovering the economically valuable components of the battery. And today that's typically the metals. So it's the nickel, the manganese, and the cobalt. And so the processes that they're using are preferentially extracting those materials because, frankly, they're the ones that they can make money out of. Now, over time, we need to develop technologies, and we also need to develop a business case that means that it's worth also extracting some of the other materials, things like the graphites, things like the electrolyte materials, which also form a significant part of the value of the battery. Right now, it would cost you far, far more to use a recycled version of that than it would to buy to use a virgin material. So two things are happening. First is there's lots of research on how to develop those processes and how to make them cost effective. And the second is you can be reasonably sure that just like the end of life directive has come into place for cars that says that all of the component, or 95% of the components of a car have to be recyclable, that's regulatory driven. That's not driven by an economic case. I think you're going to start to see the same for batteries once the technologies are available to do it. Right now, a regulation to do that would not be able to go very far because the technology doesn't exist for some of those components.
And it's really, just quick final one on that, James, it's really important that the materials coming out of the battery can go back into a battery. At the moment, the chemicals and minerals used in the battery are chemically engineered battery-grade raw materials. They're not just any raw materials. So actually making them the quality to go back in the battery is probably going to be the biggest challenge for recyclers going forward.
Yes, there's a question here.
Right. So in the traditional model we've grown up of producing vehicles, the idea is the more you produce, the less they cost per unit, or you can add frills and things on for the same cost. It seems to be what you're saying with these giga ones, and then logically latching on the rest of the reduction to it, that the more you produce an unlimited amount of ethically sourced material, the more you produce, the more you shove up the unit price.
So from a manufacturing perspective, clearly the same rules of economy of scale apply to an extent, which is why the gigafactories are the size they are. But that only covers the cost of converting the raw materials to the final product. And clearly, as the market ramps up, and Simon showed the scale of the ramp up the market needs to achieve, you're going to see times in there where the supply and demand get out of kilter with each other. And that is inevitably going to drive some price fluctuations. So the issue might not just be that the price could increase at times, but also that it might not be terribly predictable. I think Simon's probably a better place to comment on that.
On the ethical side of things, usually if you want ethical raw materials, the price goes up. It's a really good point. Cobalt's a perfect example, for instance. Cobalt, Casper, 70%, 65% is a DRC? 70% of cobalt comes from the Democratic Republic of Congo. There aren't any big cobalt mines outside of the Congo. It's just a geological curiosity of the world. So if you want guaranteed ethical cobalt, then you can't be sourcing from the Congo, but then at the same time you want scale. So then what do you do next? You try and build new mines outside, but they're going to be more expensive. So I agree, certainly on the cobalt side and for probably other raw materials that are sourced in China, like graphite, for example, ethical means a higher cost at a time when everyone wants cost to go down.
I think there was a question here.
Could you say a bit more about batteries for general energy storage, electrification, because power generation, I think, is a much, much bigger thing to worry about than cars?
So at the moment, from a battery industry perspective, cars is where it's at. And the reason for that is because cars are a market which are very highly regulated towards reducing their CO2 and their pollution. The technology has got to a point where it can start to answer that question, albeit at a relatively high cost point, and the volumes are very significant. So right now, that is, if you're a battery manufacturer, right now, that's the market that you really care about capturing. Now, in theory, grid scale energy storage could be about the same size or even a larger market. The challenge is it's a slower one at the moment, and the regulatory regimes in many countries, the UK included, are such that actually ownership of energy storage assets is quite difficult within the system. So our current regulations do not allow distribution network operators to own batteries because they're classed as an energy generation device, and the regulator wants to separate generation from distribution. So the one organisation in the UK that could take a benefit from owning that device is prohibited from using it, from buying it. So it is a really important market. It will come. It may not use the same technologies that we develop for cars. In cars, we care a lot about safety and the compactness of the battery. If you're going to put your battery in a large remote building connected to a wind turbine, you can deal with things like safety differently. You don't care about mass, and you probably don't care about volume so much. So there are very different technologies that we would start to develop for those when the market builds to be ready for them.
In the last few years, the energy storage industry globally has grown fourfold, but it's from a really low base. It's like 5 gigawatt hours worth of battery market last year. It was about 160 gigawatt hours, of which nearly all of those were lithium-ion batteries. And that's not necessarily because it's the best fit for the purpose. It's because it's available and the cost is coming down. Other battery technologies that are competing in the space, as I mentioned, lead acid, vanadium flow. But for me, the scale of the build out of these battery mega factories will mean the availability will go up, the cost will come down, and that market will emerge, lithium-ion will emerge in that market even stronger, I think.
This is related to the last question, but could you say a word about the power infrastructure required to recharge the car batteries? First of all, the power stations or renewable energies which will be capable of supplying that, and secondly, the distribution networks.
Mm-hmm. Would you like to pick that up?
No.
So the first question, the first part of that question, I think, is, can the grid cope? Is there enough electricity out there to charge all of these vehicles? I think that the simple answer to that is yes, as long as we don't all plug them in simultaneously. And actually that's quite, whilst it seems superficial, actually it's quite an important point. So as the market grows, dealing with 1 million or so vehicles on the road is not that difficult. Even if we all come back and plug them in at 5 o'clock in the evening, there is enough capacity remaining with the generation network and the high voltage distribution network to deal with that. Unfortunately, if we do it, we push the generating resources to their maximum limit, and at that point we start to bring back on stream things like coal, which we've typically been trying to turn off in order to get the CO2 balance back. If, on the other hand, we can coordinate the charging of vehicles to take place particularly overnight or during the day when there's much less demand on the grid, then we do so much more cost effectively with lower carbon and in a way which is quite perfectly manageable by both the grid and the vehicle. So I think at the overall power generation level, I'm not terribly worried. Even with the grid as we have it today, there's enough capacity to be able to support pretty much a total fleet. However, we have to get it from where it's generated to where it's used. And whereas the high voltage network, the 400 kV grid that the National Grid operates, is sized around all of the power generation that we've got, when you come off that and start to distribute it around to houses, you're using an infrastructure, much of which was put in place in the 1930s or thereabouts, when the average power consumption for a house was, the average maximum power consumption for a house was 1.5 kilowatts. So in other words, the people putting the copper in your road hope that if you put your kettle on, the person in the house next door doesn't. And that infrastructure has been well used over a long period of time, and that asset has been sweated. And we're at the point now where some of the substations at the end of your road rely on cooling down overnight in order to be able to manage the rigors of the next day. And of course, if that road then produces a lot of electric vehicles all charging overnight, then we take away some of that. So my concern is less with the overall generation of power. I think that's a manageable issue. We do have some challenges. We need to get some signals protocols between charging cars and grids to say when's good and when's not, but that's not rocket science. But I'm much more worried about the local infrastructure, how we go from the high voltage grid down to a service station with a load of fast chargers on, or to a road full of electric vehicles that's got a 1930s housing stock.
One here, and then there's one at the top.
Hello.
Yes. Who's that? Yes.
Many of the questions have been about, have talked about how expensive the batteries are. Does that mean that there is always going to be a higher initial cost in buying an electric car as opposed to one with an ICE?
I think that's one for me, isn't it?
Yeah.
That is probably one of the biggest challenges we face at the moment, is how to make sure that we can really integrate the design of the battery so that we're taking out every single element of cost that is just not necessary to have in the vehicle. Mentioned earlier in terms of the $100 per kilowatt hour in terms of the sweet spot. At the moment, that's the sweet spot that people are chasing for cells. Ultimately, we need to get to that level at the pack level, which then means that we're looking again at how we integrate the cells into the modules and then into the packs and into the overall vehicle. All of that is challenging for the automotive manufacturers, and we're all chasing that sweet spot of $100 per pack level. Is ultimately what we need to get to, which is the value which we understand is parity then with a petrol or a diesel. Until that point, yes, electric vehicles will be more expensive, which is where we therefore need the subsidies that we can see within the market at the moment. And we need that in order to then be able to get to the point where we have that volume, we have the scalability. Another point earlier I think was mentioned in terms of standardization, and that really is key for us as well. We can see we've got cylindricals, we've got prismatics, we've got pouch, we've got different levels of chemistry. For those of us who remember, it's the VHS Betamax discussion going on at the moment in the battery world. That is the arms race which is taking place that Simon mentioned right at the beginning. And ultimately, we will come to a point where we have the capacity, we have the scale, we have the standardization, and that will then drive the cost to the point where we have a competitive vehicle which is on a parity with the petrol or diesel that you have today.
And at the moment, if your battery fails after 8 years, you're looking at a bill of £30,000 for a new battery on your car, and a Tesla.
Once it's out of warranty.
Yeah.
Okay. Can I just say something on value? You
Yes.
mentioned value, that there is value to be had from other avenues as well, that you've public perception and acceptance of a new technology, that you feel like you're buying into something that environmentally is very sound and that you're doing something good for the rest of the world. by buying an electric vehicle. So there's value in terms of how much it costs to actually make these cars and how much value you place on buying them. But there's value as well in the uptake of these new technologies by society as a whole.
And from a performance perspective, they're bloody cool. Like if you get in a Model 3, for example, you put your foot down, you won't go back. It's a completely different experience. But just a final point on that question, at a time when electric vehicles haven't really been a thing, battery costs have crashed effectively. In the last 4 years, have gone from $280 per kilowatt hour to now at Tesla under 100. The average in the industry, production cost this is, average in the industry is about 140 right now. So that's a significant drop without the perceived volume in the market. So the trend is going that way, and it's really just a matter of time.
Yes.
So don't forget, your standard petrol and diesel car is not going to continue being the price it is today either. As you've seen all of the news around air quality emissions, you'll see increasingly stringent air quality targets. That's mandating a fairly big chemical plant on the back of your engine today that costs about the same as the engine itself. So there's a crossover point at the moment predicted with the trajectory of battery price coming down and the trajectory of internal combustion becoming more expensive. And depending who you talk to, that crossover point is somewhere around the late 2020s.
Okay, I think we had a question up here somewhere.
Yeah, the question I was going to
possibly
ask
two.
fits
I don't
in.
know if there's.
Sorry,
do you want to ask one as well? Yeah. So one up there, and then one down here.
The question I was going to ask kind of fits into the direction of the conversation, which is historically there's been a lot of talk about fuel cells and hydrogen as alternatives to internal combustion engines. Do they have a role with the battery, or is it just exogenous generation of power and then storage in a battery, or do you have other kind of propulsion devices in a car? As I say, maybe a fuel cell or a hydrogen source.
So I'd say a battery has a role in a fuel cell. So typically a fuel cell is sized to provide the average power of a vehicle, and then a fuel cell vehicle typically has a battery on board as well, which accommodates accelerations and regenerative braking events. So the two technologies in some way are complementary. On the other hand, one fundamentally takes its energy on board in the form of electrons, and the other fundamentally takes its energy on board in the form of a hydrogen gas or liquid. I have my own views on that. I'll expound on them later if necessary, but I'm sticking with batteries for now.
Do you want to come in, Judith or Serena, on this one or not?
I think it kind of goes back to the earlier question about energy storage as a whole, and for an whole energy system. I think we've been talking mainly about cars, but when we move to an electrified future where we're reliant on renewables, any energy system that we have is going to be hybridized. So you're going to see spots for all of these technologies, and everything is going to have to integrate quite seamlessly together. And that, again, we were talking about interfaces earlier. Getting those interfaces between technologies is going to be a great challenge for not just scientists and engineers, but for companies as well.
Hi, thank you. You sort of asked, the previous question kind of asked what I was going to ask, but I think what I was interested in was where the UK is actually trying to strategically place itself, because it sounds like we're chasing at the heels of things that have already been done. So the gigafactories exist and they're already pushing down the prices. So in terms of like where the Faraday Institution focuses its efforts, is it focusing its efforts on an engineering issue, or is it focusing its efforts on new materials? Because it sounds like the panel is a bit undecided as to whether they can come to meet the targets that the UK has for electric vehicles on the road.
Okay, who wants to quickly answer that one? Serena, do you want to tackle that?
I think, I've shown some of the history of where lithium-ion batteries came from, and there's so much rooted here in the UK, from the work that Faraday did up to John Goodenough's work on discovering lithium cobalt oxide and the birth of lithium-ion batteries. So we have a rich history from which to grow from. And what the Faraday Institution projects are looking at the moment, it's like a mixture of what you're talking about. We're looking at fundamental problems that we're trying to solve in terms of preventing degradation in battery materials, to discovering the next generation of all solid-state batteries, to looking at how you might manufacture these materials at scale. So I think there's no one silver bullet to any of this. It's a combination of approaches. And one of the things that the Faraday Institution's done really well is pulling in all of this expertise from across multiple universities, multiple departments, multiple industry partners, policymakers, to try and make sure that we approach all of these problems with a really holistic, in a really holistic way. So it's not just that chemistry is going to make the big breakthrough, or physics or engineering. It's a combination of all of those subjects and all of that expertise that the UK has to offer that will bring about the next generation of lithium-ion
And it's so often the case, actually. I mean, the UK is actually a very good research base for this. The research is world-class. We need to turn that into world-class ability to deliver this at scale. I think we've probably only got time for 2 quick questions. I don't know who is next here. Yes, thank you.
I have a quick question for Simon, and your wonderful graph on the Gigafactory pipeline. I just wanted to know that immediate sort of future capacity that you depicted, is that being driven by any particular battery chemistry? And a quick follow-up question on that, the average cost of the battery, is that being driven by a particular battery chemistry at this moment in time?
Yeah, it's a good question. The vast majority of that, essentially everyone but Tesla, is NCM or NMC chemistry, which is nickel, cobalt, manganese. Now, within that, there are various ratios of that. The industry has gone from 111, which is 30% nickel, 30% manganese, 33% of each, basically, to right now it's 523 and 622 of NCM, the C being cobalt. The holy grail is to go to an 811, which is really high nickel, 80%, really low cobalt, 10%, and that's the holy grail. But the problem is when you build these 811 batteries, you get greater density. The car can go further. It costs more money because you have to build an entirely new line in the battery facility because of the way it's produced is different with low humidity. So that's the trend for 95% of that capacity. Tesla is an NCA. It's naturally low cobalt anyway. It's lower than that 811. I would say those are the things that are driving all of that capacity.
I think we are out of time, unfortunately. I know lots of people who want to ask questions. You're going to have to come up and nab people individually. I might take Chairman's prerogative and ask one question that I've been dying to ask all evening, which is, whenever it's cold, my iPhone battery runs out very quickly. Is that going to happen to the car?
Recently there were reports in terms of the capacity certainly reduces when the temperature goes down. And that's really where the battery management systems come in, and the need to precondition the batteries before so the vehicle and
in
warm
cold
the battery
weather,
up.
what's the likely distance that you'll be able to go in the I-Pace?
Oh, it depends on many things. I know I'm hedging the answer here. It will certainly reduce, but it really will depend on the terrain you're driving in, how many people you've got in your car. There's an awful lot, but there will be a percentage reduction in very cold weather.
And these auto guys, they want you to have good batteries in your car because they want that to last a long time.
Exactly.
People that make the phones don't want you to have good batteries. They want you to change it every 2 years.
Yeah.
And that's a fact. So like anything in portable energy doesn't have very good batteries, and that's a strategy. It's different for the automakers.
It's very different.
Thank you all very much for a very stimulating talk.
Thank you.